Hi everyone. This video is a follow-up to section 5.3 at the request of a student. We're just going to go through example 4 and 5 again with a little greater detail in terms of how you go about each of the steps. Okay, so we have to diagonalize this matrix A, and as I said in the original video for section 5.3, we need to find the eigenvalues first. Eigenvalues. There we go. That's our first step. So in section 5.2, we said, all right, I need to take the determinant of a minus lambda times the identity, set it equal to 0. So what does that look like? How do you, the student, do that specifically? We'll go back and rewatch 5.2 or listen right now. So I am going to set up the matrix A minus lambda times the identity, right? And since it's lambda times the identity, we subtract along the diagonal, subtract lambda along the diagonal. So that's my first row. -3, -5 minus lambda is my second row. -3, and then 3, 3, 1 minus lambda is my third row. Okay, so that is my A minus lambda I matrix. To actually do this determinant of A minus lambda I, this would be a lot to expect you to do by hand for this example. So this is one where I would absolutely use my calculator. Hit that second math button and then go to determinant, and then you are going to type in this matrix in your calculator. Okay, if you do that, when you get to the lambdas, use some other dummy variable. I just typed in x, so along each of those diagonal entries, 1 minus x, -5 minus x, 1 minus x. Okay, so you can just find the determinant of A minus lambda times the identity in your calculator, and it actually gives it to you in factored form. So my calculator spits out negative parentheses. It says x, but I'm going to write down lambda minus 1, lambda plus 2 squared. Okay, so that was calculator work. You're using your TI-89. Okay, so this is equal to 0 when lambda equals +1, or when lambda equals -2. And because we have that squared there, that means that -2 has a multiplicity of 2. Just add a comma there. Okay, so that's the first step. So that's what you would do. You could do the determinant by hand, but that would be a little bit ugly, a little bit challenging for this example, for this setup of matrix. Then we get to step 2, where we are going to look for, hopefully, and find 3 linearly independent eigenvectors. All right, and I said in the video, this goes back to section 5.1, where we are going to now solve A minus lambda times the identity, x equals 0. So we're going to take our, individually, take our 2 eigenvectors, lambda equals 1, and subtract 1 times the identity. So for my original matrix, 1 minus 1, 3, 3. I'm subtracting 1 because that's the eigenvalue. -3, -5 minus 1, -3. And then 3, 3, 1 minus 1. Okay, so we subtract 1 along the main diagonal. And then you get 0, 3, 3, -3, -6, -3, 3, 3, and 0. All right, that is the A minus lambda I matrix. So then we're going to solve this system, the homogeneous system, A minus lambda I x equals 0, right? So we would do some row operations. Well, let me write it out first. I'm going to switch the first and third rows. So 3, 3, 0, -3, -6, -3, 0, 3, 3. Augment with a column of zeros, and then perform some row operations. All right, so I'm going to maybe scale row 1, and this is one where you can absolutely use your calculator again. Okay, I scaled row 1. I'm adding rows 1 and 2. This gives me a 0 here, -3 here, -3 and 0. And I'm going to scale row 3 also, 1, 1, 0. All right, so then my next row operation, let's switch rows 2 and 3. 1, 1, 0, 0, 0, 1, 1, 0. And also, I can see that rows 2 and 3 are almost identical, but that's going to give me a free variable, right? So if I triple row 3 and add row 2, that gives me the 0 there. One more row operation. Use the 1 in the middle row to eliminate the 1 above it. And what do? You negate and add. So that makes this become 1, 0, negative 1, 0. So negate row 2, add row 1, 0, 1, 1, 0. And then my row of zeros, like that. All right, so now to represent our solution, all right, our solution x equals x1, x2, x3. We can see that x3 is our free variable. There's no pivot there. x2, so now I'm looking at the middle row, x2 would equal negative x3. And then x1, looking at the top row, would equal positive x3. Factoring the x3 out, times 1 minus 1, positive 1. Okay, and that is where in the video for section 5.3, that is where I ended up with, and I acknowledge that I was skipping lots of steps there. Okay, but this is one you use your calculator to help you look back in your notes and all that. That is where I said, all right, my first eigenvector, 1 minus 1, 1. 2 more eigenvectors to go. I'm going to scroll over this way and say, all right, now for my eigenvector lambda equals negative 2, eigenvalue, excuse me, lambda equals negative 2, I'm now going to set up the matrix A minus negative 2 times the identity, and that minus negative becomes A plus 2i. So I'm adding 2 along the main diagonal. 1 plus 2 is 3, 3, 3 in row 1. Negative 3, negative 5 plus 2 is negative 3, negative 3 in row 2. And then 3, 3, 1 plus 2 is 3 on the bottom. And look at all that, craziness. So when we augment that with a column of zeros, 3, 3, 3, negative 3, negative 3, negative 3, 3, 3, 3, 0, 0, 0. Oh, I just noticed I made a mistake up above. Sorry about that. That should say A plus 2 times the identity. All right, back to my matrix. This reduces, you can see how rows 2 and 3 both get eliminated. Row 1 I can scale. All right, and because now I have those two free variables, I know I'm going to produce 2 linearly independent eigenvectors. So it's at this moment that I know that my matrix is diagonalizable. Right? We found 3 eigenvectors. Right? That was good. Right now is when we know that the matrix is is diagonalizable, because I'm going to get enough eigenvectors. Okay, so what are my eigenvectors here? So I represent my solution just like I did previously. x1, x2, x3. We can see that x2 and x3 are free because they're missing pivots. x1 is negative, x2 minus x3, and that is how we'll get our other 2 eigenvectors. x2 times minus 1, 1, 0, and plus, let me move over a little bit here, x3 times, what is that, minus 1, 0, and positive 1. Okay, and those are my 2 eigenvectors. All right, that I got in the 5.3 video. I said V2 was minus 1, minus 1, 1, 0, and V3 is minus 1, 0, 1. Okay, actually, I'm just realizing, I'm looking back at my video, I labeled them with different no, I fixed the subscripts. Okay, good. I thought I made a mistake, but no, I did not. All right, so that's, I think, hopefully enough detail there. Okay, so now to kind of close this problem out, V1, V2, V3, those form the columns of the P matrix. We can use our calculator to find its inverse, and then our diagonal matrix is formed by the 3 eigenvectors. Okay, that's it for this one. Now I want to look at the next example, which I'm noticing is also titled Example 4. That's weird that they're both called Example 4. But I'm not going to go through all of this, okay? Just point out what makes this matrix diagonalization different than the previous one and why this one is not diagonalizable, okay? So in step 1, you find the determinant of a minus lambda I, use the determinant button in your calculator, subtract the lambda along the main diagonal, and you come up with this characteristic polynomial. It looks the exact same as the previous example, just the way the math of this one works out. We get the exact same characteristic equation. So lambda equals positive 1 and lambda equals negative 2 with a multiplicity of 2. Lambda equals positive 1 doesn't work out any differently than it did in the previous example. Okay, so that's not the unique part of this problem. But when we try to find eigenvectors for lambda equals negative 2, let's see what happens. So I'm going to take a minus negative 2 times the identity. So we're going to subtract 2 along, or excuse me, add 2 along the diagonal. We get 4, 4, 3. Negative 4, add 2 to negative 6, also get negative 4, negative 3, and 3, 3, 3. All right, so what happens there when we augment it with our column of zeros? 4, 4, 3, negative 4, negative 4, negative 3, 3, 3, 3. Augment it because we're solving a minus lambda I times x equals 0 to find that eigenvector. Well, this reduces. You can see rows 1 and 2 are identical. So I have 4, 4, 3, 0. Rows 1 and 2 are identical, so that gives me a row of zeros. But that isn't also the case with rows 1 and 3. Those are not identical. So I'm actually going to scale row 3 and get 1, 1, 1, 0. And then let's do another row operation. I'm going to switch rows 1 and 3. Drop my row of zeros to the bottom. Hopefully I'm not doing too many things at once. And now I'm going to take negative 4 times that, add that. Okay, that's going to give me a 0 here. Negative 4 times that. Oops, I should use spread. Negative 4 times that. Add that. It's going to give me a 0 right there. Negative 4 times that. Add that. Negative 4 add 3 is negative 1. And 0. Okay, so we don't we don't lose 2 pivots as we did in the previous example, allowing for the 2 linearly independent eigenvectors. We only miss 1 pivot. All right, so I can scale that second row, so now I have a positive 1 there. And when I go to represent the solution to this system, x equals x1, x2, x3, we can see that now our free variable, our missing pivot, is x2. It looks like x3 is equal to 0. Oops, and I didn't show this step. I should have. I apologize. We would also use this pivot here to eliminate the 1 above it. So that's technically a 0 there. All right, so I should have shown that. So the reduced echelon form looks like this. 1, 0, 0, 0, 1, 0, like that. And then 0, 0, 0. Okay, I missed that step. So our x3 is equal to 0, x2 is our free variable, and x1 would equal negative x2. And that there is where we got our pivot, or our eigenvector was -1, 1, and 0. Okay, because I didn't lose a second pivot, I don't get 2 linearly independent eigenvectors, and that's why this matrix is not diagonalizable. All right. Hopefully that helps to see some of the details of what's going on here. If you have any questions, especially if you are the student that asked to see this problem drawn out in more detail, please let me know. Thank you very much for listening. Have a wonderful day.